So yeah, my name is Kostas. I'm 33. Numbers are here important because a couple of days ago, now I can't remember exactly when, but either it was Wednesday or Thursday, so yesterday or the day before, I had 10 years anniversary since I set the foot into a Danish land. And I came originally to study at DIKU and became a consultant pretty much shortly after graduating. My background, yes, is quite dynamic. I have started doing plumbing work initially, like .NET apps for Naturerhvervsstyrelsen or Movia. Then moved on to creating liquidity coverage ratio, high volume processing in native PLSQL in Nordea, and then completely redesigning it in Spring Boot and Akka. Then moved to doing a bit more exciting stuff, like together with Max in here, Android applications. We did a very interesting low-level image processing back in the day on a very early Android phones and transformed them into a film scanner. We did the first augmented reality apps for Roskilde Festival. Then moved on to creating or porting your favorite wine app to a smartwatch. Then got back to plumbing again by doing SRE together with Mikkel up there in the trade shift. And then also doing some non-coding activities like promoting the girls in IT. And that was before it was cool. Yeah, back in the day, so with Max. So I like to think that I love building software, and I'm curious about things work, and especially I love when they work. And in fact, we all know that they don't most of the time. And in this forum, people that usually are called up to fix those things when they are not working. So, first of all, problem definition. Bit of buzzwords in here. You all know that we live in a world where the software is quite complex and is distributed, usually built by people that are scattered through all the world, and the machines, that is bare metal, or virtual ones, are also scattered everywhere. And if you think about people who are troubleshooting such systems, and a typical engineer in that scenario, well, when he's looking into a latency issue, let's say he knows that the particular requests are not performing well, he might not really understand where to start with. So he don't know which component is failing. He might not even know whom to ping, because again, there are plenty of people, and those people, they work in different teams. They are scattered. They have their own tiny little adult toys, languages or what some sorts. So he doesn't know where to start or where to look at. And another issue is that some of the machines are reused for the deployment for different applications. As a result, you don't even know, maybe the artifact of latency is because of that application, or maybe because of the another. So to give you a specific example, yeah, let's say this is how a typical request looks. You have a client, and it hits the external proxy, load balance, internal proxy, and then that one calls microservice 1, that calls microservice 3, and then apparently internal proxy also called microservice 2. That one called microservice 3, then some legacy services called, and then again, some of them hit modern database, some of them hit legacy database. Now, that doesn't make much sense, but neither does most of the modern software. However, if you look at this picture, this is how a typical engineer who's troubleshooting sees it. So see, there's a client, it hit load balancer, and then bam, some like black box. I don't know what happened in there. I can see some logs in here and in here. So there's a problem. And most probably your software stack doesn't look like that. More looks like this. And these and these beautiful images of Death Star, you can see them on the web. You can just, I think the keyword is microservice Death Star. And yeah, this is some popular web shop. This is where all the millennials go for fun. And here's another one. That looks weird. I think that's Twitter. And here's one more. That was some Russian website. You can just see how beautiful it looks. But we all agree this is bullshit. However, it's the world we live in, and you cannot go around it. we have to deal with. So I think we need a tool at some point that helps us understand the system behavior and helps us maybe find the places where the performance issue occur in order to try to fix them. So distributed tracing, it's a method used to profile and monitor applications, especially those built using microservice architecture. And it helps to pinpoint where the failures occur and what causes the poor performance. So I defined you the problem and the solution. I would gladly dismiss you all here, but we probably have to go through all this agenda. So we will start by examining the origins of distributed tracing, what triggered this concept, because some of the things you will hear, they will say, okay, we are using it, we are not calling it distributed tracing. Yes, but we need a formalization. So we'll examine the original idea published in Google Dapper paper, the technology they use in their internal search engine. They formalize some key concepts for distributed tracing, which are used in the current OpenTracing, that is open source implementation of distributed tracing. And we will use one of the tools for the live demo, that is Jaeger. So, that's going to be a long one. So, if we think about the tool which would be useful in such a scenario, we have to examine two important key features that such a tool must have. It must be a ubiquitous deployment and continuous monitoring. Now, ubiquity is very important because you cannot leave out any systems, submodules, or anything within your system not monitored or traced. Because even the slight deviation might be the actual latency problem in that particular module. And continuous monitoring, that is, data is cheap, you will have to always have monitoring on, because, well, the problem occurs and it's usually very difficult to reproduce the problem. So it should be always on. And with those in mind, Google designed Dapper, their distributed tracing system. They published the paper in 2010. That paper already described their experience with this, so God knows when they started using it. But when they were designing that system, they had those three key principles in mind. So there must be low overhead. There will naturally, when you are adding some auxiliary, let's say, log points or anything to the system, there should be low overhead. There will always be, however super clever your distributed tracing instrumentation is, there will be sensitive services. So there should be zero to no impact for your existing functionality. Application level transparency is important because the instrumentation part, where you add the client additional libraries or instrumentation logic to your code, well, developers don't like it. They don't want to even think that there is some sort of instrumentation in place, and when they are developing features, that there should be some impact for that. Scalability is important, obviously, because the request amounts and data volumes are high. And for that reason, well, your distributed tracing system must be able to support large volumes of data. That's pretty obvious. And the key concepts that one must understand before we dive into the specific distributed tracing solution is these: trace and span the data, the representation for specific request, instrumentation, annotations, trace and sampling, and trace collection. Now, what are those? We need some sort of a data structure to define a request, and surprise, surprise, it's a tree. The smallest unit of work within a specific request is considered an operation, and it's called span. Now, a collection of spans or operations within your request are indeed a request, a trace tree. Edges define in that tree the causal relationship between those spans. Now, each span, as you can see, has an ID, and it has either parent ID or it doesn't have one, the root one. They all share the same trace ID, as you can see in this picture. Get more specific, let's say at some point within your trace, you have a get customer address. You can see the trace ID and span ID, and then it has two child spans, get customer and get address. So your downstream service microservice calls two other microservices to get the result. And you can see they have different, all of them have different span IDs, but they share the same trace ID. Pretty simple. Yeah, the tree. Just to summarize the span, it has an ID, trace ID, timestamps of starting and ending time. Well, that's very important, by the way, because this is how we time the operations. So, and two optional features, parent span ID, if it has one, and some annotations. Oh, this is just relationships. Yes, another interesting aspect of distributed tracing is instrumentation. Now, it is very important to note that, well, there are a couple of ways to instrument. And when we design the implementation of distributed tracing within your product, we have to think and take into account two aspects, intrusiveness and automatic versus manual. But before that, we have to understand what the trace context is. And the trace context is a collection of trace and span IDs and all the information that is stored within the current request. It should be available to all the nodes that are being instrumented. The intrusiveness is very important because you always think either we instrument the actual application or natively application component, meaning we do the code changes or at least some configuration changes, or we apply a non-intrusive approach where, let's say, we implement some sidecar proxy solution where we wrap the instrumentation around the component in the deployment layer without actually doing any changes within that component. Although this looks nice on paper, I pretty much couldn't find any solutions that would achieve it. Even the commercial ones, you still had to implement the headers from the application component. So automatic versus manual instrumentation means either you make the manual code changes, well, you basically not necessarily add span starts here, do some magic, span starts ends in here, or it's more like reusing some of the already instrumented frameworks. Let's say you have a Spring Boot application and you implement a filter within all your company. You have a shared module, let's say common or something, and it's being reused across bootstrapping all your services. And there you have a filter for requests for inbound and outbound requests, and there you add the log points to each of those. You could also add some additional manually information to existing span. Let's say we already agreed that we have an ID and we have start and end time. However, we can add additional information like strings or key value pairs that will be visible when you examine the requests. In Google Apple, they call it annotations. In OpenTracing, it's called bagage, and I think in Jaeger, they even call it tags, so that might vary. Another interesting aspect to consider is sampling. So everyone says these days, and I said actually in the beginning of this presentation, that data is cheap and you should probably store all the requests. However, you probably will not do that. When me and Mikael, we were in TradeShift, I think one of the lead architects, he was quite clear that, well, we have to implement it and we have to instrument and monitor every request and store every request for many days, like at least 30 days. But I think it has some certain cons because, well, there will always be some services which are very sensitive to the overhead introduced by instrumentation. And there are clever strategies. Like Google, they used in their Dapper, in a very initial stage, at least what it says in the paper, they used simple, straightforward sampling, like unit sampling, every 1024th request. Now I think they and Jaeger and many other systems are a bit more clever. Well, that's not like super clever, but they use time unit adaptive sampling, whereas in high frequency requests you sample for lower rate, and in low request rate you sample a bit more of these, and that usually works. That's what they say. So collection, every component, when it is instrumented, when it has starting and ending times, it reports to storage. That's where you save everything. There are several, that's actually how it looks in layman's terms, but I'll get back to the exact cool implementation when we get to the Jaeger. So far we had a lot of talk on text size. This is a picture. This is where you exactly would like to end. So imagine you have this picture and you have a initiated request, and you have every component with timestamps when it was hit and it stopped executing his part of the request. You can see the causal relationships chaining and child of, so you have the services, which in terms go corporate and legacy, and that calls some other stuff, and eventually you even have the SQL statements, and I think that's pretty neat. However, this is not the real picture. This is something that, well, I have charted with Google Charts. So, but at the end of presentation, we will arrive to the actual one. So, the publication of Google Dapper paper spawned very nice initiatives in industry. And someone at Twitter decided to build Zipkin. That's the first widely available commercial system. It was later open sourced. And it was a proprietary implementation, very hugely inspired by Google Dapper. Later, Uber implemented something called Jaeger and open sourced it. Unlike Twitter, they chose a path of going open source and open tracing straight from the beginning. So what is open tracing? And like they say in their website, and I would agree with that, it's much easier by explaining what it is not. So it's not a program that you can download and plug in somewhere and stuff starts working. And apparently it's not a standard either. So Cloud Native Computing Foundation are not an official standard body. So they only have a comprised set of APIs, language-specific APIs. They have a set of recommendations and documentation, which, if you use all these tools for your distributed tracing implementation, then you have open tracing compliant solution. Now, what does that give you? Well, first of all, there's no vendor lock-in. Imagine if you have instrumented your application, you are using some commercial product. It's not necessarily open tracing solution that is free. And you would like to switch to an open source one like Jaeger. Ideally, if all goes fine, and you're stuck to the open tracing recommendations, you can avoid having any compile time changes, only switching the runtime dependencies, and have a different system doing the instrumentation. This is how it works in a nutshell. You have a couple of processes. There's some RPC call, which has auxiliary open tracing payload. Now, this part of the picture I'd like you to focus. Here we have this open tracing interchangeable API, and then we have some client libraries specific to a proprietary open tracing implementation, say Jaeger. And that's essentially what open tracing is. It's available for these languages, but it's important to note that it's not that, let's say, I have a Java application and I have to develop from the very, I don't know, from very basic points, the instrumentation. For each of these languages, the open source community has implemented a bunch of frameworks, framework-ready, bootstrap, automatic instrumentations. We will, in the demo, use one of them. So, we have arrived to a specific OpenTracing implementation. Jaeger, yeah?
Do they succeed in being unintrusive?
I have no idea how to answer that. Define unintrusive.
Java. Yeah, okay. How difficult is the Java plugin to use? Do you have to write a lot of code, change a lot of?
No. But it depends which framework you are using. For a simple, I don't know, Spring Boot application, you can, if you only want to have a wrapped component instrumentation, meaning this microservice, inbound request, outbound request, time that. You can get that without any code changes using only automatic bootstrap configuration. You add a Jaeger dependency to your POM file, compile time dependency, bam, it works. No code changes at all. But that's because this is a very popular framework. There are cases where I'm pretty sure, well, for instance, like we worked with Mikael in Tradeshift, and there they had a Scala component which was doing the reverse proxy. That was proprietary implementation. Unfortunately for me, I had to instrument it. And for that, there was no let's say, no help, no framework at all. But I was not familiar with Scala. But I don't consider that was a difficult task to wrap it and do the chaining to propagate the trace context further on. So for that exact company previously, I did the pros and cons matrix for many popular open tracing solutions. You'll have to trust my word. You can do it yourself actually, but you have to trust my word that the most mature one right now, the open source one, not commercial one, is Jaeger, the one that was developed by Uber. And why it stands out from the others? I think it's because it fully supports open tracing. Well, it's open source and supports open tracing. It has a bunch of client-ready libraries. And while it's implemented in Go, that's not probably a good argument, but I think it also applies or implies that a certain quality of the people devoting their time to this project. It's CNCF-backed project, again, like companies like Apple and GitHub are in this foundation, and they don't kind of incubate lame projects. So, and more importantly, it's Kubernetes ready. Now, why that's important, I'm going to tell you in the next slide. Apparently, Jaeger is a distributed system itself. Now, it comprises of several components. And in this simplified picture, you have your application. By application, we probably mean some of your microservice or a single unit deployed somewhere. Then you have an instrumentation running on it as a part of your code base at the compile time. It's called Jaeger client. That Jaeger client pushes through the UDP all of its spans to Jaeger agent. Now, that's a network daemon, probably, hopefully, deployed somewhere on the same host as your application. It batches a bunch of spans and pushes them to the Jaeger collector. That unit receives through probably TCP a bunch of, yes, it's a proprietary implementation of TCP that they use, a bunch of spans. It indexes them and saves to database, data store. One way or another, it's also providing the information which spans should be saved and which not by providing the sampling information directly to the agent. And it's important to note that the Jaeger supports multiple, before mentioned sampling strategies. They are possible to change at the runtime, and I actually tested that, so it works.
Do you have to besides instrumenting the client
Yes.
that you want to trace, you then have to set up more servers, or you have to set up one server to collect the span?
That's a good question because it's up to you. Again, this is a distributed system. There is, for instance, those components are all available in a Docker hub. There's also a Kubernetes operator ready for your deployment. So it's up to you and up to your volume of data. How many instances, for instance, of collector do you need? Most probably, if you have a huge, you're serving the whole world, probably you'll have much more than one. And as for data store, I think I have written somewhere, I think Cassandra, Elasticsearch, and Kafka are supported for the data store. So I have many options also on that area. The only, let's say, non-flexible components are these. The Jaeger query component, which provides the API for you to extract, well, all this information somehow and probably visualize it. They provide a very, very lame UI, but still usable to some extent. Now, just quickly, let's dive into this part because it's where the whole interest of this talk probably. Imagine you have an incoming request and it has the trace information or trace context information within the headers. And in that specific your tiny microservice, you have a filter. Well, you kind of intercept the incoming request and then you intercept the outgoing one, and then that's how you time that span with starting times and ending times with some additional information up here. This instrumentation here in magenta, this is the OpenTracing implementation, vendor independent one. However, at the runtime, you still have Jaeger client library, some Java library that is capable of sending through the UDP stuff to the Jaeger agent. That's how simple it works. Oh yeah, demo. That's a link if some of you don't know here, open computers.
What happens if the Jaeger agent is down?
And you are not sending any. Okay, that's a good question from one aspect. So, Jaeger agent is here. The purpose of this agent to, of course, handle some overhead problems. Let's say the UDP transactions are one way, and it's very easy to push a lot of data without really caring whether it is captured or not, right? Now, if it's down, no one is forwarding those. And that's, well, a problem. You are losing this information. If you want, why I'm getting here, it is possible, and the creator of the Jaeger original guy that implemented it, Yuri Shkuro, I have been reading a lot of his posts, and he provided a method of pushing through, again, from proprietary TCP implementation from the client directly to the collector. It is possible.
I was thinking about the business application.
Yeah.
Will it get an exception or will it continue its
No, it will continue to work. You, of course, will see in the log of Jaeger agent that there is a problem, but it does not impact the application itself. So I'm gonna do a demo with actual code. I hope this will succeed. It's a Spring Boot application. It's a Spring Boot application, and it has an architecture in here. Yeah, there's a client, a person who comes to a cinema, and he wants to see a repertoire of the cinema, what movies are shown, and the cinema. Apparently, it's a microservice. It calls a distributor, which is another service who provides the movies and has what movies are available, and that one apparently has a database, and that database has some movies. So, very simple. Let's maybe try to examine the code first. I have some. Very good. So that's a cinema application. And to prove the point, yes, there is a single endpoint called repertoire. It calls movie service. Now, if we look at the movie service, just to prove, here we have a movie list operation, which in turn calls the distributor to get the movies. Now, this is tiny note, which is become relevant a bit later on. There's a circuit breaker in case the distributor stops providing movies. The cinema theater can show the in-house fantastic film Sound of Music. And to prove the point even more, we have a, what was it called? Distributor application. And the distributor application, single endpoint, movies, blah, 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 and it just queries the database. And apparently, yeah, comma-separated list of films. Very straightforward things. If we will have time later, we can jump back to this. That's enough of the code presentation. So this is an instrumented Spring Boot app. I haven't shown you how I instrumented it. You can't see any instrumentation in here. Maybe it's because all of it is somewhere else. I have, some of you asked how difficult it is to instrument it. This is how difficult it is to instrument it. I have a bunch of dependencies, 2 of them actually, in my configuration. No code changes at all. Let's see how it works. Let's do a GET request. See, well, it returns 4 films that are available. That most probably came from distributor. Now, if we Max was very kind to prepare at some point Docker image for that one. Sorry. Let's say the distributor is stopped, and apparently Cinema will no longer have films from it. And it shows the Sound of Music from its own repertoire. Now, why did I do these 2 requests? Well, ideally, I should see them in here. So this is this lame Jaeger UI that I was telling about. Here you have some sort of strange user interface, but you can, again, you can build your own. But in here, you can choose which service you would like them to get information from, which operations. Yeah, timing, some filtering maybe by tags, packages, and yes. So it says that a minute ago there was this request, and this is how long it took, 14 milliseconds, quite impressive. So we hit the Cinema GET repertoire, which in turn hit the distributor to the movies. Then in the distributor we had a database query, and that query resulted, well, into this. You have all this information already available to you. And we had done another request, which apparently did not succeed. And you can see the error codes. Yeah. So that's how simple and how cool Jaeger is. There are more OpenTracing tutorials on this website, and you are very welcome to check them out. This is something that, together with Max, we prepared them. There's this Spring Boot tutorial. It's, yeah.
Will this also work with reactive code? So if you have, this has a filter, right? But if you have a reactive code where you have React4j or something like that.
Yeah, but probably there is someone who already implemented a wrapper for that. And if not, it will definitely work with reactive code if you do your own library or add implementation of OpenTracing into your code base.
And open source.
And open source.
Yeah.
So I presume that there's already something baked into, in this case, Spring, that acts on these things and inserts the relevant sort of calls at some point, thus creating the span.
Yeah.
in a worst case scenario, if I have some other code, I work with some relatively obscure library or so on and so forth, there I can just fall back to this sort of standard API and create these spans myself.
Yes.
Right?
Yes.
Okay, so I can instrument my own domain.
Oh yes, that's very important. Exactly. Because why is it important? We only discussed so far the cases, let's say if we focus on Spring, of inbound and outbound requests. But within single span, you are welcome to create the sub-spans because you probably have some, let's say, operation which takes longer time, right? Some clever magic you are doing here, some algorithm or whatnot. In here, you can add additional starting spans and even subspans of those. So there are no limitations for that. Yeah. So coming back to these tutorials, there are a couple of cases covered. This was the Spring Boot that I just showed you. There's a client side, so you can actually have the requests also coming from the client side. There's a React.js app, so what you saw in the Spring Boot, additionally to that, the span starts from the client side. So it's a purely JavaScript implementation. And there's a vendor-independent OpenTracing example where you have a OpenTracing MPI used at the compile time for the implementation. But we show how to use a runtime dependency interchanging the Jaeger with OpenZipkin. So without, again, any code, even compile time changes, only the runtime changes, you can switch between two vendors. And there's also an example of deployment using the Kubernetes of Jaeger plus the Spring Boot application. This is a book which I would like to recommend. And like many wise people, like Schopenhauer and the rest do, I'm going to recommend you a book without reading it. It's the best you can do about the book. No, but it's a brand new book. The reason I'm recommending it is because of this guy. So again, he created Jaeger. He is very active. I'm often reading his posts, both on Medium and in GitHub. He's active on GitHub, and he is your best resource if you want to understand something about OpenTracing and Jaeger. And just one moment.
Would you say he's a Jägermeister?
He is the world's best Jägermeister for now. The reason I'm referring to this book, there are a couple of topics I haven't covered today, and I think they are important and interesting. So tracing with service mesh and integration with metrics and logs. These two topics, I think some of you would be highly interested in that. How to do the non-intrusive tracing implementation using OpenTracing. I don't know. From what I've read in his blog post, that's doable. From what I read other than his posts on the web, it's only the commercial solutions that are capable to do right now. And integrating with the existing logging system, I think this is kind of interesting topic that probably most of you would be interested to follow up. And since these slides will be shared, I've added a couple of useful links. Those are the topics that we've covered. OpenZipkin is the branch solution of the original Zipkin, which is OpenTracing compliant. And this specific just is, I think, one of the best resources I found on the web on understanding distributed tracing and current range of solutions for distributed tracing. It's not new. And I think it's published a year ago or something. But that guy, Mr. Adrian Cole, if you dive into distributed tracing, you'll find more of him. He is the original developer of Zipkin. And he is very active in both communities, apparently on OpenTracing and the proprietary Zipkin. And he shares a very polarized opinion of distributed tracing. And here, it's not a long post. If you want, you can just read it. He explains the pros and cons of OpenTracing and all the distributed tracing implementations. Because today I present you something which is super fantastic. You all should use it and blah, 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 blah. But not necessarily that is true. And I think this post might give you a different opinion. I'm done.
Right.